Section 1. The Cosmic Abyss, an invitation to the impossible. Fall into 1. Imagine yourself adrift in the silent emptiness of space. You are approaching an object of such immense power that it defies our everyday understanding of physics. This object is a black hole. It is a region of space-time where gravity is so strong that nothing can escape, not even light. It is the final, collapsed remnant of a massive star, a cosmic ghost left behind after a spectacular death. This journey, though purely a thought experiment, is one of the most profound trips we can take. It pushes the limits of our knowledge and forces us to confront the very nature of reality, space-time itself. A black hole is not a hole in the traditional sense, nor is it empty. It is an incredible amount of matter, squeezed into an impossibly small space. Think of a star 10 times more massive than our Sun, crushed down into a sphere the size of a city. The result is a gravitational field so powerful that it warps the fabric of space-time around it. This warping is the key to its strange properties. It creates a one-way door into the unknown. Once you cross its boundary, there is no turning back. Your destiny is sealed, and you are pulled inexorably toward the center of this cosmic enigma, a place where our laws of physics break down completely. At the heart of this discussion are two fundamental concepts: the event horizon, the singularity. The event horizon is the black hole's point of no return. It is not a physical surface you can touch, but rather an invisible boundary in space. Imagine it as the edge of a waterfall. Once your boat drifts past that edge, you cannot paddle back upstream. You are committed to the fall. For a black hole, this boundary marks the point where the gravitational pull becomes so overwhelming that the escape velocity exceeds the speed of light. Nothing that crosses it can ever get out again, forever trapped by the immense gravity. Deeper inside, at the very center, lies the singularity. This is the theoretical endpoint of your journey. Here, according to our current theories, the matter of the original star is crushed into a point of infinite density and zero volume. Space-time curvature becomes infinite. All the known laws of physics, including Einstein's theory of general relativity, cease to make sense at this point. The singularity represents a breakdown in our understanding of the universe. It is a place where space as we know it ends and time as we know it end. What truly lies there remains one of the greatest unsolved mysteries in all of science, a question we are still striving to answer. Section 2, Charting the Unknown, Questions at the Edge of Space-Time. This journey into a black hole naturally raises some of the biggest questions in physics. The first and most basic question is, what creates these cosmic monsters? How does nature forge an object so extreme that it can swallow light and tear apart the very fabric of reality? The answer lies in the life and death of the universe's most massive stars. When these giants run out of fuel, their own gravity overwhelms them, causing a catastrophic collapse. Black holes are not just theoretical curiosities. They're a natural and necessary part of the cosmic life cycle, shaping the galaxies they inhabit. The second major question is one of evidence. If black holes are truly black, trapping all light, how can we possibly know they exist? We cannot see them directly. So how have we become so certain of their presence throughout the universe? The answer is that we observe their profound effects on their surroundings. We see stars orbiting seemingly empty points in space at incredible speeds. We detect intense X-rays from gas being heated to millions of degrees as it is pulled in. We have even recorded the ripples in space-time, gravitational waves, created when two black holes merge. These indirect clues provide overwhelming proof that these invisible giants are out there. This brings us to the ultimate question, the one that ignites our imagination. What would actually happen if you fell into one? What would you see and feel on this one-way trip to oblivion? This is where the physics becomes truly mind-bending. Your perception of time would warp dramatically, compared to someone watching from a safe distance. Your body would be subjected to immense gravitational forces that stretch and squeeze it in a process gruesomely named spaghettification. The journey across the event horizon would be surprisingly uneventful from your perspective, yet it would mark the moment you are forever disconnected from the rest of the universe. In this essay, we will embark on this thought experiment step by step. We will explore the science behind these phenomena in clear, simple language. We will start by understanding how black holes are born and how we find them. Then, we will take the plunge, describing the journey from the perspective of the unfortunate traveler and from the perspective of a distant observer. We will navigate the strange effects on time, light, matter, separating what science knows for certain from what remains speculative. This exploration will not only explain a fascinating cosmic object, but also reveal deep truths about the fundamental laws that govern our universe. Table of Contents, Part 2, Act 1. What are black holes? 1. The force of creation, gravity's ultimate triumph. 2. Anatomy of a monster, mapping the key regions. 3. Cosmic heavyweights, the different classes of black holes. 4. Stellar collapse, the violent birth of a black hole. 5. Finding the invisible, the evidence for black holes. Section 1. The force of creation, gravity's ultimate triumph. To understand a black hole, we must first understand gravity. Gravity isn't just a force that pulls an apple to the ground. It's a fundamental property of the universe itself. Albert Einstein's general relativity, gravity is curvature of spacetime caused by mass and energy. Imagine a flat, stretched-out rubber sheet. Place a bowling ball in the center. The sheet bends, creating a dip. That dip is like the warping of space-time around a massive object. Star, planet. A smaller marble rolling nearby is drawn into the curve, circling the bowling ball like the Earth orbits the Sun. Matter tells space-time how to curve, and that curvature tells other matter how to move. For most objects, this curvature is gentle. Planets, stars, entire galaxies. These are dips other objects can escape with enough speed. A rocket leaving Earth's gravity well. Light from distant stars bending slightly past the sun. But if immense mass is packed into a tiny volume, the dip in the space-time sheet deepens. At a critical density, the dip becomes bottomless. A puncture in the fabric of reality from which there's no escape. This is the black hole, gravity's ultimate triumph. The critical point is the Schwarzschild radius, named for Carl Schwarzschild, who solved Einstein's equations. The radius marks how small a mass must be compressed to form a black hole. Everything with mass has a Schwarzschild radius. U, the Earth, the Sun. For Earth, about the size of a sugar cube. For the Sun, about 3 kilometers, just under 2 miles. No known natural process can crush Earth or Sun to those densities. Their internal pressures resist collapse. But the most massive stars are different. Giants, many times the Sun's mass, reach the end of their lives. They run out of nuclear fuel that held them up for millions of years. The outward push from fusion ceases. Gravity takes over in a sudden, catastrophic victory. The star's core collapses under its weight, squeezing matter past the point of no return. It shrinks within its own Schwarzschild radius. In that moment, a black hole is born. The dip becomes an abyss. The event horizon springs into existence, sealing that region from the cosmos. Section 2. Anatomy of a monster. Mapping the key regions. While the singularity and the event horizon are the defining features of a black hole, its immediate surroundings are also shaped by extreme gravity. The most famous of these is the accretion disk. This is not part of the black hole itself, but rather a collection of gas, dust, stars, other matter, all captured by the black hole's gravity, but not yet crossed the event horizon. This material does not fall straight in. Instead, it spirals inward, forming a flat, spinning disk like water down a drain. Intense friction and gravitational forces heat the disk to millions of degrees, causing it to glow across the electromagnetic spectrum, especially in X-rays. That glowing makes the accretion disk one of the most luminous phenomena in the universe. It is this light that lets us indirectly see a black hole. As matter nears the event horizon, it orbits at incredible speeds, approaching light speed. The disk's inner edge marks the last stable circular orbit. Any closer, and matter makes its final, swift plunge. Powerful radiation and magnetic fields from the disk can launch colossal jets from the poles, jets that travel near light speed, stretching thousands of light years. These jets are dramatic signposts of a black hole. Just outside the event horizon lies the photon sphere. Here gravity is so strong photons are forced into orbits. A photon moving tangentially at this distance would be trapped, circling forever. Stand there and you'd see the back of your own head. The photon sphere is unstable. A slight perturbation sends photons spiraling in or flying off. This extreme light-bending warps space around the black hole. For spinning black holes, there is the ergosphere, an oval region of spacetime just outside the event horizon. The black hole's rotation drags spacetime, frame dragging. Inside the ergosphere, you cannot stand still relative to a distant observer. You would be forced to rotate with the hole. It's theoretically possible to enter the ergosphere and escape, extracting rotational energy, but it's an incredibly treacherous place at the very edge of oblivion. Section 3. Cosmic Heavyweights. The different classes of black holes. Black holes are not all the same. They come in a variety of sizes, which scientists group into several main categories based on their mass. The most common type is the stellar mass black hole. These are the direct remnants of massive stars. They typically have a mass between about 3 and 100 times that of our Sun. Even though they're many times heavier than the Sun, they are incredibly compact. A stellar mass black hole with 10 times the Sun's mass would have an event horizon about 60 kilometers across, about 37 miles. Our Milky Way is thought to be teeming with them. Astronomers estimate there could be as many as 100 million of these silent predators. On the opposite end of the scale are supermassive black holes, behemoths with masses from millions to billions of suns. Their origins are a topic of intense scientific debate, but we know they sit at the centers of most large galaxies, including ours. Sagittarius A star, the Milky Way's central black hole, has about 4 million suns. Its event horizon is large enough to fit inside Mercury's orbit. The black hole imaged by the Event Horizon Telescope in M87 is far larger, weighing about 6.5 billion solar masses. Between these classes are the mysterious intermediate mass black holes. Thought to be between 100 and 100,000 suns, they bridge the gap. For a long time they were only theoretical, but recent evidence has begun to support their existence. They might form from mergers of multiple stellar mass black holes, or from runaway collisions of massive stars in dense clusters. Finding them matters. They could be the seeds of supermassive black holes. Different sizes mean vastly different experiences for anything falling in. The key difference is tidal forces, the stretching from gravity. Around a small stellar mass black hole, gravity changes extremely fast, producing huge tidal forces well outside the event horizon. An astronaut falling in would be torn apart long before reaching the point of no return. Around a supermassive black hole, the gravitational slope is much gentler. Tidal forces at its event horizon can be weak enough that an explorer crosses intact, only to meet their end much deeper inside. Section 4. Stellar Collapse, the Violent Birth of a Black Hole. The formation of a stellar mass black hole is one of the most dramatic events in the universe. It begins with a star at least 20 to 25 times more massive than our Sun. For millions of years, this star shines brightly, powered by nuclear fusion in its core. Hydrogen atoms fuse into helium, releasing enormous energy. Helium fuses into carbon. Carbon fuses into neon. The star moves up the periodic table, trying to support its weight. The chain stops at iron. Fusing iron consumes energy instead of releasing it. The core fills with iron, and the energy source is gone. Outward pressure vanishes. Gravity wins. The core collapses catastrophically in a fraction of a second. The outer layers lose support and come crashing inward at speeds approaching a significant fraction of light speed. They slam into the ultra-dense core and rebound in a titanic supernova. The supernova briefly outshines its host galaxy. It blasts the outer layers into space, enriching the interstellar medium. Those heavy elements will later form new stars, planets, even life. The fate of the core now depends on its mass. If the core exceeds about 3 solar masses, no known force can stop collapse. Not electron degeneracy pressure, the white dwarf support, nor neutron degeneracy pressure, the neutron star support. Gravity becomes all-powerful. The core shrinks past its Schwarzschild radius. The event horizon forms, a black hole is born. The core's matter is crushed toward a central singularity. The supernova fades, leaving a silent, invisible remnant. A once brilliant star becomes a tiny region of warped spacetime, a gravitational ghost. This violent death and rebirth drives galactic evolution and is the main way the universe makes stellar mass black holes, seeds for future cosmic structures. Section 5. Finding the Invisible. The Evidence for Black Holes. Since black holes themselves are invisible, astronomers must become cosmic detectives, searching for the clues they leave behind in their environment. One of the earliest and most compelling pieces of evidence came from observing X-ray binaries. These are systems where a normal star is in a close orbit with an unseen compact companion. The powerful gravity of the companion pulls gas from the star, which then spirals into a hot accretion disk. As we've learned, this disk gets heated to millions of degrees and emits intense X-rays. By measuring the orbit of the visible star, astronomers can calculate the mass of its invisible partner. If the mass is greater than 3 times that of the Sun, the object is too heavy to be a neutron star and must be a black hole. Another powerful method is to watch the orbits of stars in the centers of galaxies. For decades, astronomers at the Keck Observatory and the Very Large Telescope tracked the movements of stars near the center of our Milky Way. They saw these stars whipping around a seemingly empty point in space at incredible speeds. One star, named S2, completes its orbit in just 16 years, reaching speeds of over 25 million kilometers per hour, 15.5 million miles per hour. The only explanation for these rapid orbits is the presence of a supermassive object with immense gravity. These observations allowed scientists to precisely calculate the mass of Sagittarius A star, providing undeniable proof of a supermassive black hole at our galaxy's heart. A revolutionary new window into the universe of black holes opened in 2015 with the first direct detection of gravitational waves by the LIGO experiment. These ripples in the fabric of space-time were predicted by Einstein a century earlier. The signal detected on Earth came from the cataclysmic merger of 2 stellar mass black holes that had spiraled into each other more than 1 billion light-years away. This detection was not just proof of gravitational waves, it was direct, audible evidence of black holes themselves. Since then, dozens of similar events have been recorded, allowing us to study the population, masses, and spins of black holes in unprecedented detail. It's like finally being able to hear the thunder after only seeing the lightning. Perhaps the most visually stunning evidence came in 2019, when the Event Horizon Telescope collaboration released the first ever direct image of a black hole. By coordinating a network of radio telescopes across the globe to create a virtual Earth-sized observatory, they were able to achieve the resolution needed to see the supermassive black hole in the galaxy M87. The image shows a dark central region, the black hole's shadow, surrounded by a bright, lopsided ring of glowing plasma from its accretion disk. This picture matched the predictions of Einstein's theory of general relativity with stunning accuracy, transforming black holes from a theoretical concept into a tangible, observable reality for all the world to see. Table of Contents, Part 3, Act 2, The Physics of Falling In, about 5 sections. 1. The Long Approach, A Distorted Universe. 2. Time's Slow Dance, The Observer's Paradox. 3. The Point of No Return, Crossing the Event Horizon. 4. Spaghettification, Gravity's Cruel Embrace. 5. Two Destinies, Stellar versus Supermassive Black Holes. Section 1. The Long Approach. A Distorted Universe. Our journey begins far from the black hole, in the relative safety of deep space. From this distance, it is just another point of light in the sky, indistinguishable from a star. But as our hypothetical spacecraft drifts closer, strange things begin to happen to the view outside our window. The black hole itself remains invisible, a perfect circle of blackness against the cosmos. However, the space around it becomes a cosmic funhouse mirror. The immense gravity bends the path of light from the stars and galaxies behind it, creating a phenomenon known as gravitational lensing. Stars that should be hidden behind the black hole appear distorted and smeared into arcs of light around its edge, rings of light around its edge. It is as if we are looking through the base of a giant wine glass, with the universe warped and twisted around the central void. As we continue our approach, we begin to see the accretion disk more clearly. If the black hole is active and feeding on nearby material, this disk will be a terrifyingly beautiful sight. It is a flat, swirling vortex of gas and dust, heated to millions of degrees by friction and gravitational compression. It glows with an incandescent fury, outshining all the nearby stars combined. Yet the light from this disk is also distorted. The side of the disk spinning toward us appears intensely bright and blue-shifted, its light waves compressed and increased in energy. The side spinning away from us seems dimmer and red-shifted, its light waves stretched to lower energies. This is the Doppler effect, amplified to an extreme degree by the incredible speeds and gravitational forces at play, painting a lopsided and surreal portrait of cosmic violence. The closer we get, the more the black hole dominates our view. The circle of blackness, the event horizon, grows larger, swallowing more and more of the sky. The lensing effect becomes more extreme. We might see multiple images of the same distant galaxy as its light takes several different paths around the black hole to reach our eyes. The entire universe seems to contract into a smaller and smaller patch of sky behind us, while the black hole looms ever larger in front. We are falling deeper into the gravitational well, and the fabric of space-time itself is curving more steeply around us. The forces acting on our ship are still manageable, but the visual distortion is a clear and ominous warning of the power we are approaching. At this stage, we would also feel the first gentle tugs of the tidal forces. Gravity pulls on every part of our body and our spaceship, but it pulls more strongly on the parts that are closer to the black hole. If we are falling feet first, our feet will be pulled with slightly more force than our head. This differential pull creates a stretching sensation. At first, it would be imperceptible, far weaker than the pull of gravity on Earth, but it is a relentless, growing force. It is the first physical hint that the black hole is not just a passive object, but an active force that is starting to exert its influence over us, body and soul. The journey has truly begun, and the laws of physics are starting to behave in ways that defy all earthly experience. Section 2. Time's Slow Dance. The Observer's Paradox. One of the most profound consequences of Einstein's theory of general relativity is that time is not absolute. The rate at which time passes depends on your motion and the strength of the gravity you are experiencing. This effect, known as gravitational time dilation, becomes extreme near a black hole. Let's imagine there is a distant observer, perhaps a crewmate on a mothership parked at a safe distance, watching our descent through a powerful telescope. From our perspective as the person falling, time seems to pass completely normally. The second hand on our watch ticks by at its usual pace. We feel no sense of time slowing down. Our thoughts, our heartbeat, our every action unfolds in what feels like a normal, linear progression of moments. For our friend watching from the mothership, however, the story is entirely different. As we fall deeper into the black hole's gravity well, they will see our clock begin to tick slower and slower relative to their own. If we were to send them a light signal every second, the time between each signal's arrival would get progressively longer. From their perspective, our movements would appear to slow down as if we were moving through cosmic molasses. As we get closer and closer to the event horizon, this effect becomes infinitely pronounced. To the outside observer, our fall seems to take an eternity. They would see our image become dimmer and redder as the light leaving our ship loses energy, climbing out of the gravity well. This leads to a startling paradox. As we approach the event horizon, the distant observer would see our descent slow to a complete halt. They would see our image frozen in time at the edge of the black hole, fading and red shifting until it disappears from view. From their point of view, we never actually cross the event horizon. We are simply pasted onto its surface for all eternity, a faint frozen echo of our final moment. This is because the light from our final approach takes an infinitely long time to struggle up and escape the immense gravity at the horizon to reach their telescope. The universe would age, stars would die, galaxies would merge, while our image remains seemingly locked in place just outside the point of no return. But for us, the faller, nothing of the sort happens. We do not freeze. We do not slow down. We continue our journey, passing from the outside universe into the black hole's interior in a finite and relatively short amount of time. In a very real sense, two different realities are unfolding simultaneously. In one, we are frozen forever at the boundary. In the other, we cross it and continue toward our doom. This is not a contradiction, but a fundamental feature of relativity. There is no single universal now. The experience of time and reality itself is relative to the observer. The outside universe's future becomes our past in the instant we cross the horizon, and our connection to it is permanently severed, Section 3. The point of no return. Crossing the event horizon. The event horizon is the black hole's most famous feature, the ultimate one-way membrane. It is the boundary beyond which gravitational pull makes escape velocity exceed the speed of light. Because nothing can travel faster than light, anything that crosses the event horizon is trapped forever. It is the point where the future for all matter has only one direction, and for energy as well, inward, toward the singularity. Given its dramatic nature, one might expect a violent, spectacular crossing. You might imagine alarms blaring, the ship shaking, or a flash of light marking the passage. The reality, per general relativity, is far more subtle. From our perspective as the faller, crossing would be completely uneventful. There is no wall, no surface, no signpost in space. It is an invisible, intangible line. Because we are in free fall, we would feel no force and no acceleration. Einstein's equivalence principle says gravity feels like acceleration. Free fall is like 0 g. We'd float inside our ship, just as astronauts do in orbit. We could be playing catch with a ball, and the ball would travel in a straight line. No local experiment would tell us we'd passed the point of no return. The only way to know would be to look back. After passing the horizon, we could still see the outside universe. Light from distant stars and galaxies could still fall in after us. But the view would be bizarrely distorted. The light would be intensely blue-shifted, and the entire history of the external universe would speed up and flash in a tiny, shrinking patch of sky. More importantly, we could no longer communicate with the outside. Any message we send, any light beam we shine outward, would be pulled back by gravity and unable to escape. we become causally disconnected from the rest of spacetime. That is the true meaning of the event horizon. Not a physical barrier, but a causal one. Once inside, we can no longer affect or be affected by outside events in the same way. All paths in spacetime now lead toward the singularity. Even full-thrust rockets couldn't stop our inward fall. Inside the horizon, space and time swap roles. The direction to the singularity becomes the future. Trying to move away would be like trying to travel backward in time. It's physically impossible. We're trapped by the geometry of spacetime itself. Section 4. Spaghettification. Gravity's cruel embrace. While crossing the event horizon might be locally uneventful, our journey is far from peaceful. The same tidal forces we first felt on our approach now become the instrument of our destruction. Tidal forces arise because the strength of gravity changes over distance. As we fall feet first toward the singularity, the gravitational pull on our feet is significantly stronger than the pull on our head. This difference in force creates a powerful stretching effect along our body. At the same time, every part of our body is being pulled toward the single point of the singularity. This means our shoulders are being pulled slightly inward relative to each other, creating a compression from the sides. Vertical stretching and horizontal squeezing is gruesomely but accurately named spaghettification. As we get closer to the singularity, these tidal forces grow exponentially. The gentle stretching sensation would quickly become an unbearable pull. Our bones would snap, our muscles would tear, our entire body would be elongated into a thin, streaming ribbon of atoms. Our spaceship would suffer the same fate, being ripped apart molecule by molecule. This process is not instantaneous but a relentless and unavoidable consequence of the extreme gravity gradient. It is the raw power of the black hole deconstructing matter back into its fundamental components. The very fabric of our physical being is unraveled by the warped geometry of space-time. There is no material strong enough to withstand these forces. The experience would be, to put it mildly, unpleasant. Long before our atoms are pulled apart, the immense forces would cause catastrophic damage to our biological systems. The flow of blood, the signals in our nervous system, and the integrity of our cells would all be disrupted. Consciousness would cease long before the final, complete disassembly. It is a grim and violent end, a testament to the unforgiving nature of physics in its most extreme state. The term spaghettification might sound almost comical, but it describes a process of utter annihilation where the complex structure of a human body is reduced to a simple, one-dimensional stream of particles on its final plunge. The strength of these tidal forces depends critically on the mass of the black hole, which leads to a crucial distinction in the falling experience. For a smaller, stellar mass black hole, the curvature of spacetime is incredibly steep. The tidal forces are enormous even far outside the event horizon. An astronaut falling into a typical stellar mass black hole would be spaghettified long before they ever reach the point of no return. Their constituent atoms would cross the horizon as a disorganized stream. This means they would be torn apart before they were ever cut off from the outside universe, a truly horrifying and immediate demise. The journey into a small black hole is brutal and short. Section 5. Two Destinies. Stellar versus supermassive black holes. The fate of an object falling into a black hole is not uniform. It depends dramatically on the black hole's size. As we've seen, falling into a stellar mass black hole is a death sentence, delivered before you even reach the main event. These black holes are small and dense, with extremely high curvature of spacetime near their boundary. The distance between your head and your feet can be a significant fraction of the black hole's radius, so gravity differs wildly along your body. Tidal forces would rip you apart thousands of kilometers before the event horizon. You'd be stretched into a plasma noodle with no chance of experiencing the crossing itself. Now, Let's consider falling into a supermassive black hole, like Sagittarius A at the center of our galaxy. These giants have masses of millions of suns or billions of suns. Their event horizons are enormous. Sagittarius A's event horizon is about 24 million kilometers across. Because it's so large, space-time curvature at the edge is far gentler. The change in gravity over your body would be tiny. Tidal forces at the horizon can be weaker than gravity on Earth. You could fall through completely unharmed, without noticing the transition. This creates a profoundly different scenario. For a supermassive black hole, the crossing is peaceful. You would float across the invisible boundary, causally disconnected, yet still conscious. Only once you're deep inside do tidal forces build. Spaghettification would still happen, and doom remains certain. But you'd have precious minutes or even hours after crossing before the end. That time is spent falling toward the singularity, observing a region hidden from outside. What would you see in those final moments? Physics breaks down as you approach the singularity, so we can only speculate. Some theories say you'll see the universe's future flash before your eyes. Others propose the singularity is a chaotic, churning wall of energy. You'd witness the ultimate mystery, where general relativity and quantum mechanics must unite. A fall into a supermassive black hole offers a brief, privileged glimpse into the unknown before the inevitable end. A journey from a gentle crossing to final, violent annihilation at reality's heart. Table of Contents, Part 4, Act 3, Light, Information, and Current Mysteries, about 5 sections. 1. Light's final plunge, the redshift and the blue. 2. The black hole evaporates, Hawking's remarkable discovery. 3. The information paradox, a cosmic puzzle. 4. Solving the paradox, hints from the quantum realm. 5. The next generation, future windows on the abyss. Section 1. Light's final plunge, the redshift and the blue. As we have seen, a black hole's gravity has a profound effect on light. For an outside observer watching something fall in, the light from the falling object becomes stretched out. Its wavelength gets longer, shifting it toward the red end of the spectrum. This is known as gravitational redshift. It happens because the light has to expend energy to climb out of the black hole's deep gravity well. As the object gets closer and closer to the event horizon, this redshift becomes more and more extreme. Redder, infrared, microwaves, radio waves, with ever longer wavelengths until it fades into undetectability. The object effectively vanishes from sight, its light stretched into oblivion. This same effect is what creates the black hole's shadow, which was famously imaged by the Event Horizon Telescope. The dark central region in that image is not the event horizon itself, but the shadow it casts. This shadow is larger than the event horizon because it includes the paths of all light that are captured by the black hole. Any light that comes too close gets pulled in, leaving a void in the background light. The bright ring around it is made of photons that are not captured but are severely bent, including those from the photon sphere. This extreme bending of light, or gravitational lensing, is one of the most powerful visual confirmations we have of Einstein's theory of general relativity in action. Now let's return to our perspective as the person falling into the black hole. As we cross the event horizon, our view of the outside universe changes dramatically. Light from stars and galaxies falling in after us is now plummeting down the same steep gravitational slope. Instead of losing energy, this light gains energy. Its waves are compressed, shifting it toward the blue end of the spectrum. Brilliant blue, ultraviolet, X-rays, gamma rays, creating a blindingly bright wall of high-energy radiation. This means that while the crossing of the event horizon of a supermassive black hole might be gentle, the journey's end is anything but. The infalling astronaut would be incinerated by a ferocious bath of super-energetic light and particles long before the tidal forces of spaghettification could tear them apart. It is a harsh reminder that even when escaping one form of destruction, another awaits. The very fabric of space-time conspires to make the interior of a black hole an unsurvivable environment. The light that once guided ancient sailors and inspired poets becomes a final, lethal furnace at the end of this cosmic journey. For a long time, scientists believed black holes were truly eternal prisons. Once something fell in, it was lost forever. The black hole could only grow, never shrink. This picture was dramatically changed in 1974 by the physicist Stephen Hawking. By combining the laws of general relativity with the strange rules of quantum mechanics, he made a startling discovery. He found that black holes are not completely black after all. They should slowly emit a faint glow of thermal radiation, a phenomenon now known as Hawking radiation. This means that over immense timescales, black holes can actually lose mass, shrink, and evaporate completely. Hawking's idea comes from the bizarre nature of empty space in quantum physics. According to quantum field theory, a vacuum is not truly empty. It is a bubbling, seething cauldron of virtual particles that constantly pop into existence in pairs, a particle and its antiparticle, before quickly annihilating each other. Normally, this happens so fast that we cannot detect them. However, if a pair of these virtual particles appears right at the edge of a black hole's event horizon, it is possible for one to fall in while the other escapes. The particle that falls in has negative energy, which reduces the black hole's mass, while the one that escapes becomes a real particle carrying energy away. To a distant observer, it looks as if the black hole is radiating particles, just like a hot object. The temperature of this radiation is incredibly low for large black holes. For a stellar mass black hole, the temperature is only a tiny fraction of a degree above absolute zero, far colder than the background temperature of the universe itself. This means that today, all existing stellar black holes are absorbing more energy from the cosmic microwave background than they are emitting through Hawking radiation. This means that today, all existing supermassive black holes are absorbing more energy from the cosmic microwave background than they are emitting through Hawking radiation. They are still growing, not shrinking. The process of evaporation is currently happening at an impossibly slow rate. However, the story is different over truly cosmic timescales. The time it would take for a solar mass black hole to evaporate completely is about 10 to the 67th years, a number so fantastically large it is difficult to comprehend. For a supermassive black hole, the timescale is even longer. But the theory predicts that in the far, far future, when the universe has expanded and cooled to near absolute zero, these black holes will finally begin to lose more mass than they gain. They will slowly shrink, getting hotter, radiating faster, until they disappear in a final flash of gamma rays. Hawking's discovery transformed our understanding, showing that black holes have a finite lifespan and are deeply connected to the quantum world. Hawking's discovery that black holes can evaporate created a profound problem for physics, one that we are still grappling with today. It is called the black hole information paradox. At its heart is a fundamental conflict between two pillars of modern science, general relativity and quantum mechanics. A core principle of quantum mechanics is that information can never be truly lost. Information here means the distinct quantum properties of the particles that make up an object. If you know the complete state of a system at one time, you should be able to calculate its state at any other time. It is like an unbreakable cosmic rule of bookkeeping. Now consider what happens when something falls into a black hole. Let's say you throw a book into it. The information contained in that book, the arrangement of its atoms, the story written on its pages, crosses the event horizon and from the outside appears gone. According to general relativity, it is crushed out of existence at the singularity. That wasn't a big problem when black holes were thought permanent. One could say the information is still inside, just hidden. but Hawking radiation changes everything. If the black hole completely evaporates, leaving only featureless thermal radiation, then the original information about the book is truly destroyed. That would violate quantum mechanics. It means our understanding of the universe is incomplete. This is the essence of the information paradox. General relativity says information is destroyed at the singularity. Quantum mechanics insists information is never lost. The two theories give contradictory answers, and this clash happens right at the event horizon. Resolving this paradox is one of theoretical physics' biggest challenges. Finding a solution likely requires a new theory uniting gravity and quantum mechanics, a theory of everything. Black holes are not just cosmic objects. They are labs where our fundamental laws are pushed to the breaking point. Physicists have proposed several creative, mind-bending ideas to resolve the information paradox. One early proposal was that the information is not lost but is transferred to a separate baby universe that buds off from our own inside the black hole. This idea, however, is difficult to test and has fallen out of favor. Another dramatic idea suggested quantum mechanics is wrong and information can be destroyed. Most physicists are reluctant to accept this since information conservation underpins quantum theory. A more popular view is black hole complementarity, proposed by Leonard Susskind. Proposed by Gerard T. Hooft, it says the paradox arises from mixing perspectives. For the infalling observer, information passes through the horizon without incident. For the outside observer, the information never crosses the horizon but is imprinted on it, smeared across the surface. That information is slowly encoded and released in the subtle correlations of Hawking radiation. Complementarity says both views are true because you can never observe both at once. This links to the holographic principle, which says volume information is encoded on a region's boundary. All information about what fell in is encoded on the event horizon's two-dimensional surface. As the black hole evaporates, that information is projected back into space, scrambled in Hawking radiation. The radiation isn't purely random. It holds subtle quantum connections which, if decoded, could reconstruct everything that fell in. Recent breakthroughs add support to this view. In 2019, calculations showed plausible routes for information to escape. By including the gravitational effects of particles, physicists found mechanisms transferring interior information to outgoing radiation. The math is complex, involving quantum information theory, but points to preservation of information. The debate continues, yet we're closer to resolving this cosmic conflict. The answer appears rooted in deep, quantum-level connections between a black hole's interior and exterior. Section 5. The Next Generation. Future Windows on the Abyss. Our understanding of black holes has been built on a combination of brilliant theoretical work and painstaking observational evidence. To solve the remaining mysteries, such as the information paradox and what truly happens at the singularity, we will need to push both of these frontiers even further. On the observational side, we are entering a golden age. The Event Horizon Telescope, the EHT collaboration, is working to expand its network of telescopes, which will allow it to create sharper images and even movies of black holes. This could allow us to see the motion of matter at the event horizon in real time and test the predictions of general relativity with unprecedented precision. Another powerful tool is the detection of gravitational waves. LIGO, Virgo, KGRA. These observatories are constantly being upgraded to become more sensitive, allowing them to detect the mergers of smaller black holes and those farther away. Future space-based gravitational wave observatories, like the Laser Interferometer Space Antenna, LISA, will be able to detect the gentle, low-frequency ripples created by supermassive black holes merging or by smaller objects spiraling into them. These signals could carry detailed information about the space-time structure right near the event horizon, potentially revealing subtle quantum effects that are invisible to light-based telescopes. On the theoretical front, the quest for a theory of quantum gravity continues. This is the holy grail of fundamental physics, a single framework that can describe the large-scale universe of general relativity and the small-scale world of quantum mechanics. Leading candidates for such a theory, like string theory and loop quantum gravity, offer different pictures of what happens at a black hole's singularity. They suggest that the singularity is not a point of infinite density, but a fuzzball of vibrating strings or a region of space-time foam, where space and time dissolve into their quantum components. Testing these ideas is incredibly difficult, but black holes remain our best theoretical laboratory. Ultimately, connecting these theoretical ideas with observational data will be the key to unlocking the final secrets of black holes. Will we find subtle deviations from Einstein's theory in the images from the EHT? Will gravitational wave signals from merging black holes contain echoes that hint at new quantum physics at the event horizon? These are the questions driving the next generation of physicists and astronomers. Black holes, once purely a mathematical curiosity, have become central to our search for a deeper understanding of space, time, and information. The journey to their heart is far from over, and the most exciting discoveries may still lie ahead. Table of Contents, Part 5. Conclusion, about 2 sections. 1. The Ultimate Cosmic Journey, a summary of the fall. 2. Why Black Holes Matter, from Thought Experiment to Deep Truth. Section 1. The Ultimate Cosmic Journey, a summary of the fall. We have journeyed from the safe shores of familiar physics to the very edge of the abyss and beyond. Our exploration began with the birth of black holes, forged in the fiery death of massive stars, or grown to colossal size in the centers of galaxies. We saw how astronomers, like cosmic detectives, have gathered overwhelming evidence for these invisible giants. They track the wild orbits of stars, detect the brilliant screams of superheated gas in accretion disks, listen to the gravitational ripples of ancient mergers, and have even captured a direct image of a black hole's shadow, turning a theoretical concept into a visible reality. This evidence confirms that these extreme objects are not just a figment of our equations, but a fundamental part of our universe's structure. Armed with this knowledge, we embarked on the ultimate thought experiment, the fall into a black hole. We saw how the journey is a tale of two realities starkly divided by the event horizon. For the distant observer, our fall slows to a crawl, our image freezing and fading over an eternity. This is the paradox of time dilation, where gravity warps the very flow of moments. For us, the faller, time passes normally as we sail silently across the invisible boundary, blissfully unaware of the precise moment we have become forever disconnected from the rest of the cosmos. This contrast between the outside view and the faller's experience reveals the profound relativity of space and time. Once inside, our fate was sealed. For a small, stellar mass black hole, the journey ends before it truly begins, with the body being torn apart by immense tidal forces, spaghettification, long before reaching the horizon. For a supermassive black hole, we could cross the boundary intact, granted a few final moments to witness a region of space-time forever hidden from the outside. In this inner sanctum, we would face a blinding wall of blue-shifted light before the now inescapable tidal forces stretched us into a stream of atoms. Our final destination was the singularity, a point where our current laws of physics break down and our understanding of reality ends. This journey also forced us to confront the deepest mysteries in modern physics. We encountered Hawking radiation, the faint glow that suggests black holes can evaporate over unimaginable timescales. This led us to the information paradox, a profound conflict between Einstein's theory of gravity and the fundamental rules of quantum mechanics. Does information that falls into a black hole get destroyed forever, or is it somehow preserved and returned to the universe? The ongoing quest to solve this puzzle is pushing scientists toward a new, unified theory of quantum gravity using black holes as the ultimate theoretical crucible to test the limits of our knowledge. Section 2. Why black holes matter. From thought experiment to deep truth. Studying black holes is more than just a fascinating exercise in extreme physics. It is fundamental to our understanding of the cosmos on the grandest scale. Supermassive black holes are not just passive residents of galaxies. They are active architects. They co-evolve with their host galaxies. Their immense energy output through jets and radiation can regulate star formation across billions of light years. They are gravitational anchors, cosmic engines that help shape the structure of the universe we see today. Understanding them is essential to piecing together the story of how galaxies came to be, including our own Milky Way. Furthermore, black holes serve as unparalleled laboratories for testing the laws of nature. They are places where gravity is pushed to its absolute limit, allowing us to test Einstein's theory of general relativity with a precision that is impossible anywhere else. Every image from the Event Horizon Telescope, every gravitational wave detected from a black hole merger, is a new test, a new chance to see if Einstein's century-old equations hold up. If we ever find a deviation, it could be the first crack that leads to a new and more complete theory of gravity, revolutionizing our picture of the universe once again. The thought experiment of falling into one, which began our essay, is more than just a dramatic story. It is a powerful tool for revealing the deepest truths about our reality. This hypothetical journey teaches us that space is not just an empty stage, but a dynamic fabric that can be bent, stretched, and even torn. It shows us that time is not a universal clock, but a malleable river that flows at different speeds for different observers. It forces us to confront the limits of our own knowledge at the singularity, where our theories fail and new ideas are desperately needed. The fall into a black hole is a journey to the frontier of human understanding. So while we may never physically take this one-way trip, the act of imagining it expands our minds. What is space? What is time? What are the fundamental laws that govern everything? Black holes are the keepers of these secrets. Dark, silent, impossibly dense, where the nature of reality itself is laid bare. Falling into one remains a thought experiment, but it illuminates the profound and beautiful strangeness of our universe, reminding us that the greatest adventures are those that take place in the landscape of the mind.